So, and we continue the afternoon before the lightning talks and the reception tonight at the ICTP with, I had this, co-shifts, Tamara KUCHERENKO from CUNY, and she's going to talk about thermodynamic formalism for quarter shifts.
Thank you. Can you hear me? Did I unmute myself? No? Not good? I thought I unmuted myself. I need to talk louder, is that it? Closer. Closer. Okay, let's try this. How about now? Better? Right. Oh, now I lost my clicker. Oh, here it is. All right. So let me see if I can actually point. No? Okay. All right. So I would like to thank the organizers for this opportunity to be here. This is my first time in Trieste, and I enjoyed it tremendously. So this is a symbolic dynamics talk, and I thought before I start, I got to provide some motivation for you people from beyond uniform hyperbolicity. So the motivation will be brief and informal. So I want to talk about symbolic models. So what is the idea here? You use a symbolic system which you understand very well to study some other system which you don't understand as good. And by now it is well known that uniformly hyperbolic systems can be modeled by subshifts of finite type, and non-uniformly hyperbolic systems can be modeled by countable Markov shifts. So one result in for uniformly hyperbolic systems that really stands out, that was a catalyst for that kind of explosion of further study, was result of Bowen from 1975, who showed that for an axiom A diffeomorphism, its hyperbolic set is modeled by a subshift of finite type. And the reason this works is because of the existence of finite Markov partition. So you take your hyperbolic set, you partition it into finitely many rectangles. They have so-called Markov property. Okay, so the set of rectangles will create the alphabet for your subshift, and the Markov property will create the transition matrix. And then, of course, all the properties of ergodic measures for axiom A diffeomorphism and equilibrium states for Hilda potentials can be derived from the properties of the corresponding things on the shift. And, well, the subshifts of finite type are arguably the most understood dynamical systems. A result of similar magnitude in non-uniformly hyperbolic systems was the one by Sarig. So he proved that any C1 plus Hilda diffeomorphism with positive topological entropy, well, can be, well, the set which is a full measure for any high hyperbolic measures is modeled by a countable Markov shift. So the, well, brilliant strategy of Sarig was to take the Markov partition used by Bowen and remove the requirements that the partition is finite, but keep the Markov properties. So what you get is number of rectangles is infinite, so your alphabet of the shift is countable, but you still have the Markov property, so it gets you a countable Markov shift. Okay, and due to works of Sarig, Moldin, Urbansky, and others by now, we have a good understanding of countable shifts. So the question I want to ask here is, can non-uniformly hyperbolic systems be modeled by coded shifts? And what is the advantage here? The advantage is that the coded shifts are compact and the countable shifts are not. So for compact shifts, all the ergodic theories that we know, the classical ergodic theory would be immediately applicable. And as a proof of concept, I give you the result in the paper by Diaz, Gelfand, and Rams from 2022. They proved that for a skew product with concave interval fiber maps over a shift, so the maximal invariant set where the projections of orbits stay in a given region is modeled by a coded shift. So the authors of this paper claim, and I quote, that this model has the essence of non-hyperbolic partial hyperbolicity when the center space is one-dimensional. I will get to it. I will give you all the definitions. Yeah, be patient. This is just the motivation. In fact, if I push this button, you will see that what I'm going to do is to discuss recent project and understanding coded shifts. Okay, so we'll start from the beginning. So what are the compact shift spaces altogether? So you start with a finite set, you call it an alphabet, and you look at the product space, A to the Z. So this is a set of all sequences by infinite sequences of letters from the alphabet A. This is a compact space in the usual product topology, and one matrix that is a matrix that is compatible with this topology is the following. You take two sequences, you look at the first spot where they differ, and this number n where they differ, you take 2 to the negative n, and this is your distance. So the two sequences which coincide on a large number of entries around the center are close to each other. Then you have the shift map, which is a homeomorphism on this product set, and it simply moves your sequence to the left. Then the subshift is any closed shift invariant subset of A to the Z. We denote by ln of x a set of words of length n which appear anywhere in the sequence of x. Then the language will be the union of all these words. So any finite word which appears anywhere in the sequences of x is part of the language. And finally, the topological entropy is the exponential growth of the number of words of length n which appear in the sequence. All right, so good. How do we construct subshifts? So the usual way to construct subshifts is using forbidden sets. How does it work? You look at the union of all finite words, and then you take a subset. So this F is called a forbidden set. So this is some set of finite words. And your shift will consist of all the sequences for which the the words from the forbidden set never appear in the sequence. All right? And we say that X is a subshift of finite type if it can be constructed like that for some finite forbidden set. And let's take two very, very, very simple examples, which you usually get when you look at symbolic dynamics book. So my alphabet will be 0 and 1. And the first example, we just take forbidden set to be 2 ones. So these are all the sequences where 2 ones never appear. And this is called the golden mean shift. This is an SFT because your forbidden set is finite. And the reason it is called the golden mean shift is that when you compute the entropy of the shift, you get the log of the golden mean. And another example, I will take a forbidden set which has 1 and then some odd number of zeros and then 1 again. So what do we get then? So my X is all the sequences where between any 2 ones you get an even number of zeros, and this is an even shift. And this is not a subshift of finite type. And again, this is the first example of not a subshift of finite type that you get, looking at the any dynamics book. It so happens that this subshift has exactly the same topological entropy as this subshift. Fun fact. All right, so when I first looked at symbolic dynamics, my question was, why in the world would we construct subshifts using words that never appear in the subshift, instead of constructing subshifts using words that do appear in the subshift? And we can do that. So let's construct a subshift using generating sets. I do almost the same thing. I take a set of words, set of finite words, and then I take all concatenations of those words. So I freely concatenate the words. All right? So what do I get? Again, examples on the same alphabet. The first example, let's take generating set being 0 and 0, 1. So what would I get? I would concatenate 0 and 0, 1, and I get anything except having 2 ones next to each other. So this is my golden mean shift. Now I can take my generating set to be 1 and 0, 0. Again, I can concatenate it, but every time I put 1, I have to put 2 zeros in between, so there should be even number of zeros. So I get the even shift. Ta-da! All right. Students, who can tell me why this is the way you construct subshifts in a book, and this is not the way you construct subshifts? Students? Anyone? Anyone? Come on. Dominic couldn't help himself. Students.
Anyone.
No, I said students.
You said anyone. Anyone.
All right. So as Dominic is trying to tell you, I was cheating. So you see this, both of these sets are finite, and that's why I'm fine. But if my generating set is not finite, then this set, this one, is not closed. I was trying to deceive you so much, I didn't even tell you that this is a subshift, because in general, it is not. So this set is not closed, and here's an example. You take another generating set, this time it is infinite, so you get even numbers of zeros, and you get 1, right? Then point which consists of all zeros is in the closure, because we can get to it as close as we want using like large even zeros, okay? But you cannot build point of zeros using concatenations of the words of generators. All right, but it's not a big deal, right? What we do, we close this in. And then it is a subshift. And then what I have here at the last one is, again, the even shift. Let me make it an even shift. Here you go. Because now we are all good. All right. One more thing I want you to notice that I have two different generating sets, and I get the same shift, which is to be expected. And the last thing, the reason you have this construction in the book, because this is always closed, this is always subshift, regardless of whatever set F you get. All right, so, and here's the definition. Oh, there is a question, yes?
Yeah, I have a question. Can you please elaborate on what
Good to
in case of K?
Oh, yes, of course. So here, this is a forbidden set. So this is what I do not let happen. So I don't want to have odd number of zeros. Now here is what I do want to happen. So I do want the even number of zeros. So that's the difference.
Zero there as well. I mean,
Even, zero is even.
right, so it's included, it means it's just a single one.
Yes, zero is even. Yeah, because I can, because zero is even. So it's still, even with that, I still can have
Okay.
1, 1, 1.
So number 3.
My alphabet is still finite. My alphabet is still 0, 1. So these are sequences of 0, 1s, right? So this is just going to be sequences of 0, 1s. The alphabet is finite, but the generating set is not, right? The generating set is countable. Here, those are finite. And the same goes here. Your forbidden set could be finite, and then you get subshift of finite type, or it could be infinite, and then you may not get subshift of finite type. Good? Right. So here's the definition. The coded shifts were introduced back in 1996 by Blanchard and Hensel as generalizations of subshifts of finite type. So they say that a shift space X is coded if there exists a generating set, so a subset of the language. So we look at the language and we look at the subset of the language, such that X is the smallest shift space that contains all bi-infinite concatenations of the elements of G. Okay, and we call this G generating set, and we say that X is coded by putting this G in parentheses. So this means that X is a coded shift with generating set G. There are a lot of examples of coded shifts. So all transitive subshifts of finite type and suffix shifts, which are factors of transitive factors of SFTs, are coded shifts. S-gap shifts are coded shifts. Beta shift are coded shifts. My personal favorite, Dyke shift, is a coded shift. Now, there are two more definitions which I'm not going to use. I'm only going to use this definition, but I will give them anyway because some people have preferences defining one thing or another. So you can write every shift space as a countable directed label graph. Then coded shifts are precisely those shift spaces which have a strongly connected representation. And we know that suffix shifts are represented by some finite directed label graph. So if my coded generating set is finite, I get a suffix shift. And one more definition, which was given by Krieger in 2000, so he called it a theorem. Shift X is coded if it can be approximated by an increasing sequence of irreducible subshifts of finite type. All right? Again, I will only use the first definition from now on.
So, can I ask, so generating
You take all the concatenations of the words in the generating set. You freely concatenate them. whatever you get out of it, you take the closure. Right, then it is going to be a subshift. So you want it to be the smallest subshift which contains all of them, which is the same as just taking a closure. Yes. If there exists a generating set, then it is coded. That's the definition. Yeah. There are not coded shift space. I don't know where, like, yes, thank you. A check on shift. That sounds good. Yes. Yeah. All right, so we already seen that the same coded shift can be generated by many different generating sets. And as you might guess, some generating sets are better than others. So let me explain you what I actually want from a generating set. So we fix one, and so G is a generating set, alphabet is A, still finite, and we look at the coded shift generated by this set G. So we define the concatenation set of X is the set of all concatenations, right? So what do I want? I look at X, and as long as I can split X into pieces, or I missed space here, but as long as I can split X into pieces, I start with xki, and I end up with xki plus 1, and each piece will be a word in the generating set, then my X belongs to the concatenation set. Okay, this is a formal way of writing it. Oops. I thought I wrote what it means. Okay, I didn't. So the, basically you take all...
This notation, x, ki, plus 1.
So this is the coordinate, so it's like interval, right? This is the ki coordinate of x. So x is a sequence. This is the ki term of the sequence. Okay, maybe I should write it. So this may, you take x, right? This is your, I should write big. I was sitting up there, and I know I should write big, right? So this is your small x. Okay, let's do small x. Okay. And this part is xki, and then you keep going up to xki plus 1. Right, so your x looks like this. X, I don't know, negative, whatever. I, x negative I plus 1,
Every
blah.
block that you can find in X belongs to J.
No, let me write some more. xi plus 1, blah. So this is your x, right? So you want to be able to split it into blocks so that each of them is in G.
Oh, you mean because it might be in the closure? So
Yes, right. So I want to take those guys which actually come from the concatenations. So if I look at some point in my shift space and I want to figure out whether it is a concatenation or not, what do I need to do? I need to split it into some pieces, and that becomes a concatenation, and that would mean that it's in the concatenation set. So basically my concatenation set is a set of all, well, concatenations.
taking the closure.
Yeah, before. So this is what I got before. But usually you have a space, right? And you pick a point and you want to figure out where it came from. So you want to kind of split it. Now the important property is that I would like to have, I want to be able to split it only in one way. So if I can split it, I want to be able to split it in only one way. So I want only one set of integers that split my point.
But you call it shift closure of this.
Yes, yes, that's true. And at some point I will probably write it. Okay, so what I want from my generator is that it represents concatenation set uniquely, right? So for any point, it's, the splitting is unique. right? You cannot have points which can be represented as two different concatenations of generating sets. Yeah, generating words. Okay. So, here it is. So every point in my concatenation set has a unique representation as a concatenation of generators. There was a weaker notion, right? If you look at finite words and see if they can be represented as concatenations of generators, and you want every finite word to have at most one representation, right? So this is called unique decipherability property. And back in 1986, Blanchard and Hansel proved that every coded shift has a generating set which has the unique decipherability property. So you might start with a kind of generated set that doesn't have it, then you find another generating set which produces the same shift and that has it. Now the question that was open for a while is, so this is for the finite one, can we do the same with infinite sequences? So is it true that if you've got a shift which is coded, you can find another generator which gives you this unique representability condition? And it was resolved a couple years ago by Belpier and Arestiva. So they proved that for every coded shift there exists a generating set which uniquely represents the concatenation part. So the concatenation part depends on the generating set. Yes, but for each x I pick, I cannot have two sequences ki.
For each x will have unique
Yes,
ki. Okay.
right, so I cannot have, do we have color? Yes, we have color choke. Okay, so I cannot have this, for example, somewhere, and then again, and then again. So this is not allowed. Okay, good. Maybe I should give an example, like very trivial one. If you have, like, your generating set is just this, right? This is my G. Then if I have any finite word, I know where it comes from. So I have a finite word, there is only one way I can write it, this is it. But if I have an infinite word, I don't know, right, if it continues, so if I fix it, so this one will have unique decipherability property. But if I keep going, then I no longer will be able to tell, right? Then I can, whatever. Then I can think about it like this. Not this, but I mean some sequences, right? This was actually a bad choice. If I just write this, right, then here I know, but if and I should do it like this, right? Then here I would know where it came from, but at the moment I continue, I would not know which concatenation it came from. That is a very trivial example, but that's the point. Okay. How am I doing on time? I feel like I'm going very slow. Okay, I have no idea. Anyway, so the entropies. We fix again a generating set. I remind you that the concatenation set consists of all concatenations. And now I want to see what's left. So this is the residual set, which is basically my whole shift minus the concatenation set. This will be exactly the points added under the closure. So these two sets are sigma invariant. And of course, the union is the whole space. So the approach that we have is to study the entropy on the concatenation set and on the residual set separately. One more remark, if you have an ergodic measure on my shift space, that it must either put the full mass on the concatenation set or put the full mass on the residual set. So what I want to do, I want to define the concatenation entropy of my coded shift as the supremum of all the measure theoretical entropies of invariant probability measures which put full mass on the concatenation set, and the same with the residual entropy. And of course, the variation principle tells you that the topological entropy must be supremum of the measure theoretical entropies. So the topological entropy will be the maximum between the two. Good? Okay, so the first misconception that people have when you look at the coded shift is that the residual set must be small entropy-wise. And I'm here trying to convince you that it could be really big. So we call it flexibility of the residual set. So if you give me any transitive shift, Z, which is, okay, not the full shift, all right, and any epsilon, then I can produce a generating set on the same alphabet such that the coded shift it generates has the following properties. It has a unique representation property, right? My generating set is good. Now, the whole set, Z, will be inside the residual set. Moreover, any measure of maximal and any measure which is invariant and puts the full measure on the residual set must live on Z. So from the point of view of dynamics, that's the residual set. There will be some other stuff, but dynamically, this is it. Your set Z is the residual set. And the concatenation entropy of my set is less than epsilon, so it is as small as I want. So the entropy of my concatenation set is small, and the residual set has all the dynamics. Right? So in particular, if my set has multiple measures of maximal entropy and has, well, positive entropy, at least bigger than epsilon in this construction, then my set, my coded shift will also have multiple measures of maximal entropy. So coded shift can have whichever number of measures of maximal entropy you want. And if you want examples of subshifts with whatever cardinalities of measures of maximal entropy your heart desires, there is a wonderful paper of Jerome, which is called Subshifts of Quasi-Finite Type from Invenciones, where he has like 100 examples. Where is Jerome? I remember he enumerated the examples and they just keep going. So if you want an example of a subshift with some properties, with whatever measures of maximal entropy you like, paper of Jerome. 100, I'm not exaggerating, he enumerated them, and they all have very cool properties. Whichever number you want, countable, whatever, uncountable.
There are some construction of Krieger in particular, much earlier, where he builds a subshift which is, from the ergodic point of view, the same as a lot of stuff that you can imagine, in particular ergodic measures with finite entropy.
There are any finite number of ergodic measures of maximal entropy. Yes, that is construction of Krieger. So Jerome is trying to move the credit from himself to Krieger, which is fine. But if I say the variety of examples is astonishing. So go there. I will get to actually Krieger's shift in a bit. Okay. So what do I want? Yes. Okay, so what you want from your shift is the uniqueness of measures of maximal entropy. And of course, when the concatenation entropy is small and residual entropy is big, you cannot expect any uniqueness result. Okay, so this is a bad situation. We don't want it. But we can, at the moment this is not true, then we get uniqueness. So suppose I have a coded shift where the concatenation of the entropy of the concatenation set is bigger than entropy of the residual set, then my shift has a unique measure of maximal entropy. So at the moment your dynamics is controlled by the concatenation set, you have uniqueness. And we have a formula for the topological entropy of X. It is a log lambda, where lambda is a unique solution of this equation. So you sum up over all the generating words, lambda to the negative length of your generating word, and it should be 1. And the unique solution will be e to the entropy of your X. So this formula is really fun. Let me play with it. Remember our two trivial examples? Okay. The first one was the golden mean shift. Let's compute the entropy. So according to this, right, my entropy of the shift has to be what? Has to be log lambda, where what? So the first generator has length 1. So I put lambda to the negative 1, and the second generator has length 2. I put lambda to the negative 2, and this has to be equal to 1. Okay, we rewrite it, and we solve it, and this is the golden mean. Okay, how about example 2? Remember we have even shift, which was generated by 1 and 0, 0. Okay. But now, if I apply the same formula, I need to do the same thing. The first generator has length 1, the second generator has length 2. Voila. Since I read Lyndon Marcus' book, I was always wondering why the golden mean shift and the even shift have the same entropy, because these are literally the first examples you get. And now, a decade later, I know. This is because both of them happen to have the generating sets with the same number of generating words of exactly the same length. And you get the same entropy. All right, this was fun, but actually this entropy formula has interesting history. So it first appeared in the book of Lyndon Marcus in 1989, and it was an exercise there for S-gap shifts. All right, so after that, for decades, people were using this formula for S-gap shifts, but there was no reference to a proof. Of course, if it is an exercise in a book, it certainly discourages you from publishing a proof. Okay, finally, in 2007, Spandl published a proof for S-gap shifts, but it was incomplete. Okay, after that, von Klimenaga presented two proofs which were complete, but in his blog in 2017. Now, if you want a reference, Klimenaga's blog is not going to cut it. Okay, so finally, in 2019, Garcia Ramos and Pavlov published a fixed Spandl's proof, and they extended it to a certain class of coded shifts. And what we did, we got it in the most generality possible. Okay. I don't remember what I have on the next slide. Let's see. Oh, yes, right. So I have the same result for the similar result for the equilibrium states. Let me remind you what equilibrium states are. So if you have a coded shift and a continuous potential, then the topological pressure of the potential is defined by the variational principle. So you take supremum over all invariant probability measures of the entropy. Oops, what did I write here? This shouldn't be F, I'm sorry. It should be, oh my God, everything is wrong in this thing. So this is entropy of mu plus integral of phi d mu. Okay, so this is a topological pressure. And the measure which realizes the supremum is called an equilibrium state of phi. Now, my system is compact. The entropy map is semi-continuous, so I have equilibrium states, and the only question here is uniqueness. And we do the same dance. We define the concatenation pressure as this, oh, finally it's correct. Yeah, here it is, because I typed this and I copy that. So it's a supremum of this quantity, which is called free energy, where for all the measures which put the full measure on the concatenation set, and the residual pressure is the same where the measures live on the residual set. And again, because those are sigma invariant and disjoint, the topological pressure is going to be the maximum of the two. In the paper, which I'm going to quote pretty much through the whole talk, which is my work with Martin Schmoll and Christian Wolff, we wanted to prove the equilibrium states for Hölder potentials for coded shifts, and we were only able to prove it under the conditions that the concatenation pressure is bigger than the residual pressure. Then, okay, this means that if you, the growth rate, the exponential growth rates of the words of the generator of the same length, of length n, right, is 0, right? So the number of words of the same length can grow only sub-exponentially. So we wanted this. And then we wanted that every equilibrium state of phi has non-zero entropy. So now well, this condition is essential, right? There is no way of getting around that. And the other two conditions are not essential, and we finally were able to remove it. I'm very happy about it because it was really bothering me. So now it's a new theorem as of a month ago, joined with Mariusz Urbanski, where we got the result we want to get. So as long as your concatenation pressure is greater than the residual pressure, your Hölder potential will have a unique equilibrium state. How much time do you have? 10 minutes? Need to speed up. Okay. Oh yeah, so we were not the first ones who looked at coded shifts. There were two previous papers which served as inspiration for our work. So they studied the coded shifts. The assumption of Kleminaga and Pavlov was to compare the entropies, the topological entropy of X and the topological entropy of a subshift, which is defined like this. Okay, so what is that? So you want all the sequences where if you look at any finite word, it should be a subword of some generator. So this is a subshift, and it has the properties that it's sort of the smallest subshift which contains the residual set. Okay, it contains the residual set, yes. And it is the smallest, yeah, okay. So they wanted to have the set because then this is a subshift, our residual set is not. So then could enjoy all the ways of working with subshifts, for example, word complexity functions and so on and so on. Everything that you have when you work with proper subshifts, you can have. So now the condition was that if the topological entropy of X is bigger than this, then we will get uniqueness of measures of maximal entropy. And if the pressure on the whole thing is bigger than the pressure here, we get uniqueness of the equilibrium states for Hölder potentials. So, yeah, okay. But the thing is that because the residual set is a subset of this, the residual entropy will always be smaller than the topological one because of the variational principle. And the topological one, as the moment it is bigger than the residual one, it will be the same as the concatenation entropy. So our results will apply immediately here in the conditions. But the issue here that, okay, maybe I should show the whole theorem and then I will explain what the issue is, that this set, the limit set could be really, really big, right? And we wanted to convince ourselves that our split is actually better than this split, despite the fact that we're giving up the subshift property. And we proved that if you have a coded shift which satisfies this, there is another coded shift which is slightly bigger, so that it actually equals its limit set, has the same residual entropy as before, and the topological entropy grows at most by epsilon. So this subshift is very close to the one we had, but of course the results of Klimenaga and Pavlov cannot be applied neither for the pressure nor for the entropy because of this condition. Okay, so the last piece I want to say is that we get very nice properties of the measures of maximal entropy, right? So I can give you a description of what it looks like. So for that, I need to explain what are so-called G cylinders are. So the first definition is a regular cylinder. So if you have a word, the regular cylinder is what? You fix the first, whatever, coordinates of length G, and you make them all the same as word G. That would be your regular cylinder, right? Okay, now the G cylinder, you want to do the same thing, but you only want to do it on the concatenation set. So you look at all concatenations where the first entry in your concatenation is that specific word G. So this is my G cylinder. Okay, and that's what I just said. And of course, as the same way as you could do with regular cylinders, you can write cylinders with like a bunch of generating words. Okay, so this set depends on the choice of the generating set, so we call it G cylinders, and one can prove that these are Borel sets, that if I have any word, then the regular cylinder of this word is a disjoint union of the shifted G cylinders, and that therefore if I have any measure which lives on the concatenation set, it is determined by its mass on the G cylinders. Okay, good so far. I'm starting to speed up, which probably means I'm going to lose people. All right, so now we have G Bernoulli measures. So what are those? They behave like Bernoulli measures, but on G cylinders. So you get positive numbers which sum up to 1, the same number as your generating sets, right? And some constant. So that if you want to know the measure of a G cylinder, which looks like this, you just need to multiply PGs. And that, if it would be just multiplication, it would be exactly Bernoulli measure, but we have that normalizing constants, and then you divide by constant. It's kind of looks like Bernoulli measure, but it's not. So we call this measure G Bernoulli. And the theorem says that if my coded shift has a good generator, and the concatenation entropy is bigger than the residual one, so this is when we have the measure of maximal entropy. Then I tell you exactly what it looks like. It has to be G Bernoulli, and this numbers, PG, is very easy to compute. You just take e to the negative length of G times the entropy of X, and the normalizing constant, just the sum of all of them. Okay. And that gives me a corollary that if I have a coded shift and it has a measure of maximal entropy, but it lives on some subshift, then I can never find a generating set which would satisfy this condition. So whichever generating set I pick, the concatenation set of X will be less or equals than the residual set of X, so I can never do anything good. Oh, yes. So the curious case of the Dyke shift. So this is the result by Krieger. He was the first one to show that there is a transitive shift, which is a Dyke shift, which has two measures of maximal entropy with full support. This is a shift which is kind of a standard counterexample to show that all the theorems on coded shifts do not work. It has all the pathological conditions you can dream of. For example, for the Dyke shift and its canonical generator, we have that X equals to X slim, concatenation entropy equal less than the residual entropy, and it has two ergodic measures of maximal entropy. Okay, despite all of this, we still can say something about the measures of maximal entropy on the Dyke shift. Let me tell you what it is. How am I doing on time? Ooh. Okay, so let me not tell you what it is. Okay, so, okay, maybe just a little bit. So the Dyke shift has an alphabet of 2 parentheses and 2 brackets, and the allowable sequences are the ones you would guess. So every parenthesis should be closed by a parenthesis, every bracket should be closed by a bracket. And this is the result of Krieger that I just said. And here's a canonical generating set, which is very famous. The number of words in the generator of lengths n is actually a Catalan number, which has a name. Okay, so this is a canonical generating set. And with respect to this generating set, I have that the concatenation entropy is less than the residual one and everything fails. But, blah. Okay, we can recode the Dyke shift. So we can give a different code. So with respect to the different code, my concatenation entropy will be exactly the residual entropy. And the measure of maximal entropy, one of them, there are two, will be G Bernoulli with respect to the first code, and the measure of maximal entropy, the other one, will be G Bernoulli with respect to the second code. And I can stop there. I can just skip all the questions that I had for you and go here and click on thank you.